Hello viewers and welcome to iTTV. I hope you're having a good day. Are you ready to start a new lesson with me? Let's begin then. This lesson is a continuation in Chapter 1 of the Form 4 Additional Mathematics syllabus. Chapter 1 is the chapter on functions, and we have had several lessons before this on this topic. But in today's lesson, we're going to go into the subtopic of composite functions. Composite functions. In mathematics, the application of one function to the results of another is known as the composite function. In a composite function, the range of the first function becomes the domain of the second. Do take a look at the diagram on this slide. As you can see, set A would be the first bubble, which is the domain, that means the values of x. And if you apply the function of f, you will obtain the values of y, which are found in set B, the second bubble. Now, if you continue to apply another function, which we will call g, to the values of y, we will produce yet another answer, which is set C, the values of z. This is what we call a composite function. Set A is the domain of fx. Set B is the range of fx. But set B also happens to be the domain of gy. That's when we introduce another function called g into the system. And that will produce set C, which is the range of gy. Determining the composite of two functions. The composite function of f to g is represented by g fx. This takes a bit of getting used to, viewers, because in the diagram, f seems to come before g. However, in the notation that you see in the statement given, we should write it as g fx. What this means is that we need to apply the function of f onto the values of x, as you can see in the diagram. Hence, that is why f appears before g. And only after that, we apply the function of g to the values obtained from the first application. So in set notation form, it should be written as g fx. Do remember that the letter that is closest to x should be the function that is used first. G fx is commonly read as any one of the following three. You could either say g of f, or g follow f, or g after f. You could use any of these methods of expressing to indicate the composite function. Determining the composite of two functions. This time around, in the diagram, you notice that the function g is applied to x values firstly, producing the y values, and then the y values are replaced into the function of f to produce the z values. Therefore, the composite function that is resulted is now called f of gx. Do you notice, viewers, that the function closest to the letter x is g? Because on the diagram, we are told that the function g is applied first. Hence, take care that you know how to write the set notation for the proper composite functions. The arrow diagram shows the composite function of functions f and g. And in this particular example, the diagram shows us that the function f changes the x value of 2 into the y value of 4, and the x value of 3 into the y value of 9. Hence, the function fx is equal to x squared. Secondly, the function g converts the y value of 4 into the z value of 3, and the y value of 9 into the z value of 8. What has happened? It appears that we have subtracted 1 from each y value, and hence the function gx is equal to x minus 1. Let us take a look now at how to express the composite function. If fx is equal to x squared and gx is equal to x minus 1, With the function f being applied first, the composite function is represented by the notation g(f(x). The composite function g(f(x) would be the function that first squares the number and then takes away 1 from the result of that. And that is why g of f(x) is equal to x squared minus 1. Let me show you in more detail how this composite function can be obtained. Let's examine those two object values from the example in a bit more detail. We were given the two values of 2 and 3 and how they changed respectively. In the first case, when x was equal to 2 and we applied the function of f, which is x squared, we would have obtained the y value of 4. And then, if we further applied the function of g, which is x minus 1, the value of 4 becomes that new value of x in the function. And so we have the z value obtained is 2 squared, which was our 4, minus 1, giving us the answer 3. Again, if the second object value that was given in the diagram was x equals to 3, upon application of the function f, which is x squared, we would have obtained the value of y, which is 9. And upon application of the second function g, which is x minus 1, don't forget that to the function g, the y value is the x it wants to use. That's why z is equal to 3 squared minus 1, giving us the answer 8. Now what if we generalize this behavior and I used the letter x, just as it is? When you apply the function of f, you would obtain x squared, because that's what the function does. And to the function g, x squared is the value of x that is being used. And so if you apply the function g to x squared, you would get x squared minus 1. That's how we obtain the composite function g f(x) is equal to x squared minus 1. Let's discuss a few more examples. In this example, we are given two functions which are f, which maps x onto x squared, and g, which maps x onto 1 over x plus 3. Do take note that a condition for function g is that x cannot be equal to negative 3. Now viewers, I wonder if you know why such a condition needs to be placed. When x is equal to negative 3, that would be dangerous to the function of gx, simply because x equals to negative 3 will create a denominator value of 0. And whenever we divide anything by 0, we will have an undefined answer. Sometimes we call it an infinity case, but the actual meaning of that is that there's just no value that we understand. So that's why x cannot be equal to negative 3 in cases where there is a denominator with an expression in there. What we need to do is to find the composite function of fg and gf. Having cleared the air about the two functions given, let's look at our first step, viewers. Firstly, we must understand what f of g means. F of gx is equal to applying the function g into the function of f. What this means then is, as you can see from step 2, we need to replace gx with its image. What does that mean, viewers? Well, what does gx do? Gx changes x values into 1 over x plus 3. That is the image for the function of gx. That's why f of gx means f of 1 over x plus 3, because 1 over x plus 3 is the result of conducting function g. Moving along, the third step would be to write the function of f without any x's first, and that is to say, just prepare brackets for wherever there is supposed to be the x term. So f bracket equals to bracket square. Why is that so? Because the function of x is actually x squared. Therefore, it now allows us to fill in the brackets with the proper x that we were using. And in this case, if you refer back to step 2, the x value that was being used was 1 over x plus 3. So replace that expression into the brackets, giving us f of 1 over x plus 3 equals to the square of 1 over x plus 3. Hence, the function of f of gx is equal to 1 over x plus 3 squared. Again, do remember, viewers, we should always state that x cannot be equal to negative 3 in this case, for the reasons explained earlier. The second composite function we would like to examine is g of fx. And as always, g of fx means that we must apply the g function to the fx function. So which is the function that should be conducted first? It is the function that is closest to the letter of x, that is f. So f changes x into x squared, and therefore the image resulted from fx is x squared. That image becomes the object for the function g. As you can see, that's the reason why we want to find g of x squared. Prepare the function again by writing out gx, but changing the x into a bracket, because we are going to replace the bracket with the object that g wants to apply the function to. And the object is x squared, as was found from the function of f. Therefore, x squared goes into the bracket, and that's why g of fx is equal to 1 over x squared plus 3. In this particular instance, the denominator of x squared plus 3 does not need any condition, because x squared plus 3 will never be equal to 0, and hence we will never have a problem of an undefined case. So the function can be written as 1 over x squared plus 3, just as it is. Remember, viewers, that since x squared is always more or equal to 0, then x squared plus 3 will certainly never be negative. Now guess what, viewers? I have a surprise for you. This example that I'm going to discuss with you soon is going to be a challenge of whether you have understood what we've discussed in this lesson or not. So I would like you to try this example out by yourself for a few minutes and then come and check with us on the board. fx is equal to 2x and gx is equal to 3 minus x squared. What do you think will be the final result of the following composite function? f, g, f of x. I'm sure that will give you some thought. That's a bit unusual, isn't it, viewers? I'm sure that will give you something to think about. And secondly, I'd also like you to try out the composite function of g, f, g of x. Well, off you go to work. Come back in a few minutes and we'll discuss the answers together. Now, viewers, don't be alarmed that there are more than two functions in this composite function. The steps are still always the same. We always start with the function that's closest to the x. Or, if you're not too sure about that, always start with the letter on the most extreme right of the expression. That means we want to apply the function f first. So we are looking at f of g of fx is fg of the function fx. Now, what is fx? Fx produces the image of 2x. Hence, we can now change fx into 2x. What this means then is that the next function to apply onto this image is the function of g. But to the function of g, 2x is its object. So we will have to apply 2x into the function of g, which means that we want to put in 3 minus, careful, the x that the function g sees is 2x. If this is confusing to you, then here's a neat little trick. Just for a moment, convert 2x into a single letter like m or k. And so if you see f of gm, it would mean that wherever you see the letter x, it should be replaced with that letter m. But in actual fact, m is 2x, and that's why we end up with 3 minus 2x squared. So, before we jump into that final function of f, let's expand this, giving us 3 minus 4x squared. So this time, to the function of f, 3 minus 4x squared is its object. It's like saying that this whole thing is an x to the function of f. So what does the function of f do? The function of f changes x into 2x. Therefore, the function of f will change this entire thing into 2 times of itself, giving us 2 times 3 minus 4x squared. And so the final answer is 6 minus 8x squared. If we write it out as a conclusion, we can say that f of x is equal to 6 minus 8x squared. That's it for part A. How did you fare? I hope you got the right answer as well. Let's move on to part B now. The composite function involved this time is gf(gx). And as you know by now, gx is the first function we should apply to the object of x because it is the letter that is closest to x. And what is gx? Gx is that function 3 minus x squared. So now we are telling the composite function that we have to apply, I beg your pardon here, we have to apply the function of f into this object called 3 minus x squared. What does the function of f do? It changes the object into 2 times of itself. Hence, we are seeing that it becomes 2 times of 3 minus x squared, producing the answer 6 minus 2x squared, that the function of g needs to be applied to in the end. So what does the function of g do? The function of g changes an object x into 3 minus x squared. And to this function of g this time, its object is 6 minus 2x squared. So we should apply 3 minus x squared would be its object squared. So 6 minus 2x squared is what we should apply in there. This will require some expansion. And going by our usual quadratic expansion, we will have 36 minus 24x squared plus 4x power 4. Simplifying it gives us negative 33 plus 24x squared minus 4x power 4 as our final result. So to conclude properly, viewers, gf(gx) would be that answer, negative 33 plus 24x squared minus 4x power 4. Were you alright, viewers? I hope you have been able to follow this example and to get this answer as well. In this lesson, we've been discussing composite functions, and since this was our first time looking at this topic, we had to understand what composite functions are and how to find the composite function when you're given the individual functions. I'll see you then on our next lesson, viewers. Take care for now, and goodbye from ITTV.